Okay. All right. Give this one a. Actually, okay, by the end of this lesson, you'll be able to describe what power is and how it relates to current, voltage, and resistance, and be able to calculate an electric bill. Give that one a shot. It is. It lasts. It lasts a while. Yeah, well, that'd be heavy. The climb up. All right. So, last semester, when we were talking about power, introduced the idea that the units were watts, and some of you are like, wait a minute, isn't that what's found on light bulbs? I said, yes, it is, but let's hold off until next semester. Specifically, let's hold off until today. So, each of these are plugged into 120 volts. That's just kind of the standard in a house, pretty much across America. Okay. So this is a 40 watt light bulb, 60 watt light bulb, 100 watt light bulb, and a 200 watt light bulb. $40, $60. This is pretty standard, 60 watt light bulb. Okay. 100 and 200. Okay. All right. So now you got blue dots. So what the wattage is describing, so the answer to this is what? B, 100 watts. So what this is describing, power, is how quickly the rate at which energy, electric potential energy, is being converted into a different type of energy. In this case, with the light bulbs, it's heat and light. Okay, so these are incandescent light bulbs. Now, the old school light bulbs, our nation is transitioning away from these. Okay, because they're really inefficient in terms of producing light. I'm throwing this out here. Roughly 80% of the energy goes to heat. Only 20% goes to light. It might even be less than that. Okay. There's actually a building in New York back in the, I don't want to say 60s or 70s, that was designed not to have a heating system, but just had a bunch of lights that they left on all the time. That was the heating system. That was like really efficient for the time. It was like, it worked great. Yeah. So they just left the lights on all the time. That was the heat. The heat generated from the light bulbs heated the building. Okay. Was state of the art back then. Now it's kind of like, dude, we're going away from those. You need a heating system in your building. But so that is why LEDs is where we're going. Okay. So the fluorescent lights, you know, I don't know if you remember like seeing like the green packages, like it's a fluorescent, like the swirly lights. Okay. Funny, those have mercury in them. And that's does wonders for the environment. It's funny how they pack just I guess, be skeptical when someone's like, "Hey, this is green." Like, really, explain exactly why, and they'll have a reason, but that's probably not the whole story. Okay, those are actually worse for the environment, in my opinion, than all these over here. Like, we can burn some fossil fuel, but throw some mercury in the ground, like that's heavy metals. That's not. You don't mess with that stuff. Okay, so LEDs. Um, uh, they're designing LEDs because our houses have these fixtures in them. We need to design LED lights so that they are compatible with what we have currently in our house. So this would be um, when you go into the store, they'll say, "Hey, this is equivalent to a 60-watt light bulb," because people paying money, like me, know what a 60-watt light bulb is, and we haven't figured out. And they'll say, "Well, it's really 13.5 watts, but it's equivalent to how much a 60-watt light bulb would produce. Light it would produce." Okay, so if you ever break one of these open, it doesn't have a filament. Okay, this is just the diffuser. If you ever have a lamp with a lampshade, you take the lampshade off. It's like, oh, piercing light. Put the lampshade on it. It diffuses it and makes it. Okay, that's what this does. Okay, inside of here are just those orange dots are LEDs, light emitting diodes. Okay, they're semiconductor. So, like, I don't know if you ever heard, we have a semiconductor plant coming in the next 5 years. You all, like, some of you might be working there. I don't necessarily know if they design LED lights, but it's a semiconducting material. But these are the things that light up. And the reason why it's better is it's way more efficient. So most of the energy goes into making light. Not much. A smaller percentage goes to heat. They do get hot, but it's not as much. They're durable. They last longer than our incandescents. Okay, so this is bright, but if you squint, you can see the ring of LED lights. Okay, so now that I put blue spots in your eyes, okay, so that's just kind of want to give you some background there. All right. So, power. It's the rate at which energy is converted. Has units of energy is in what? What unit is energy? Joules, and time is in, which is what a watt is. And then I gave you this equation, the second equation. It's like, hey, this also calculates power. And like when I was in your shoes, I'm like, okay, no idea how those two connect or relate at all. I'll do the math, but all right, whatever. I want to show you how they connect. Okay. What is the unit for current? What do we measure current in? Amps. Which comes from what units? What makes up an amp? What type of units? What was it? Coulombs over seconds. Coulombs per second. Okay. And voltage is measured in what units? Voltage is measured in what unit? Volts, which is a unit which comes from what units? So voltage is how much energy there is per electron, how much energy per electron is contributed. So that is in, that's supposed to be a hint. energy is measured in joules, and electrons are measured in coulombs. It's a charge. Math people, do you see what happens? Coulombs cancel. And you're left with joules per second. Okay. So conceptually, here's how this plays out. So voltage, electric potential difference, tells about how much energy per electron is being contributed. Okay, so let's say I'm an electron. I'm going to represent energy in terms of money. I've got $100, and every electron behind me has $100 as well. We have a certain amount of energy per electron, have a certain electric potential. As we go by the resistor, we give some of that energy to the resistor. So let's say I give $80 to the resistor. Okay, that would be my electric potential difference, how much energy is being contributed each electron. Okay, so if I give $80, and the next guy behind me gives $80, and the next guy behind me gives $80, okay, I can figure out how much energy. But if I know the rate at which the electrons are passing by, how many electrons are passing by every second, I can figure out if every electron is like, here you go, and I know the rate at which they're coming, I can figure out how quickly energy is being converted into a different type of energy, the rate at which energy is being converted. Okay, anyway, questions on that? For me, that was like, wish someone would have done that for me back in the day, but all right. Give this one a shot. Have a conversation. Correct answer is got a couple B's, got a couple A's. Got another B. Got another B. Okay. Voltage is equal to current times resistance. I'm going to take this and I'm going to substitute in for here. So I've got power is equal to current times resistance. Correct answer is B. Beautiful butterflies. Okay, bless you. That is a helpful equation, a useful equation that I'm not going to give you. Man, Smiley, you're a jerk. You know, I feel like I'll give you these two. I think you can come up with this one. Okay. So as we progress throughout the year, you know how you like learned how to ride a bike? I'm starting to let go a little more often, hoping that there'll be like, look, I'm riding. I catch it. And then I catch it. Okay, good at that. Try that one. Ooh. Thumbs up when you have a guess. Have a conversation. Correct answer is? Correct answer is A. So voltage is over resistance is equal to current. I'm going to use that and substitute that in for current. So I get A. Good with that? Okay. Another equation that is helpful that you're not going to be given, that you need to be able to pull this maneuver. Okay. Okay. You're not, if you don't have this on lockdown, your life's not over. Like, it's going to be okay. In physics, your grade's not going to be like tank because of that. It's just more of a shortcut. Okay. Tell your neighbor. Correct answer is C. Everybody go to C. Good. Next question. Tell your neighbor.
Oh, I didn't read that right. My bad. My bad. Gotta read the question.
Correct answer is B. Why? Okay, and the squared makes the current carry more weight, more influential. Good? Okay. Okay. Quick leading question. What does the battery determine in a circuit? What measurement do we know voltage? Okay. The voltage is determined, the total voltage of a circuit is determined by the power supply. Okay. And we're not changing out the battery. The battery is consistent. Thumbs up when you have a guess. Tell your neighbor what you think. I sure can. So this symbol here is a battery, positive and negative terminals. These are wires that connect the battery, and this is your resistor. In this case, the light bulb, or it doesn't say that, just, yeah, resistor. It's whatever the appliance is that's using electric energy. Oh, here's another thing. The word dissipated is just the weird word that we use, the verb we use for power. I wouldn't necessarily choose it, but if you look in any physics textbooks, they all use dissipated from like, all right. So it just means to like give off, changing that energy. What do you say? Got some B's on the table. Consensus B. All right, so I'm going to show you mathematically and conceptually. So we just came up with these two equations for power. Because voltage is consistent from one side, like throughout the experiment, which of the two equations are we going to use? The right or the left? If the voltage is consistent, if you have something, a measurement that's consistent, that's gold when it comes to problem solving. Okay, because what that means is you can hold that variable stationary. It doesn't change. Okay, so this is not changing. So I can know with absolute certainty if I change this, that's going to change. If I change that, that's going to change, because this is being held still. If I have three variables that can all change, I don't know. Does that make sense? Okay, so I'm going to use this equation And so if the resistance is going up, what's going to happen to the power? Decreases. Mathematically, that's how you do it. Conceptually, so as you, so this, I mean, you could do it, you could range Ohm's law like this or like the fraction form, but the voltage is staying the same. As the resistance goes up, what happens to the current? Goes down. Does that make sense, just conceptually wise? Okay. And so, again, voltage is staying the same. As current goes down, what happens to power? Also goes down. Good with that? Next problem. Comes up when you have a guess. Have a conversation.
I was gonna say, I heard A. Since 3 years ago. Because it's multiplied, you're gonna just like roll so small.
Correct answer is B is correct. Here's two different reasons. Okay, so the voltage stays the same. So again, we're going to this equation. As the power goes down, going from 1 to 2, resistance has to go up. So conceptually, voltage stays the same. As the power gets dimmer, current goes down. Voltage stays the same, current goes down. That means the resistance had to have gone up. Good with that? Okay. This next thing, right now, you don't have to worry about utility bills. Time is coming in the pretty near future where you're going to have to be paying for utilities. Okay? That is, yep. Now, so what I want to do is give you some insight into like the ins and outs of the bills that you're going to be paying, specifically your electric bill. Okay? I feel like it's my social obligation to give you like so that you know what your money is going to. You can budget well. You can like know like, oh, if I do this, this is gonna like. So you're gonna have a problem like this on the test and on the final exam. Okay, it's just straight up calculating your electric bill. Okay, so here we go. Left a 60-watt porch light on continually for a month. If the electric company charges 9 cents per kilowatt hour, how much would you be charged for that porch light in a month? Okay. So we're going to be using this equation. The light bulb is rated at 60 watts. That's our power. Calculating how much energy is being used. I'm going to convert my time into what unit? Seconds. Okay, that's our default mode, seconds. So I'm like, ooh, month, seconds in a month. Goodness, we're going to say it's 30 days in a month, just to, you know. So converting that to seconds, I need to go to hours, so 24 hours in a day. And are you okay with me just jumping to 3,600 seconds in an hour? You okay with that? 60 times 60. Okay, so 1 hour is 3,600 seconds. Okay, so I find that time to be a lot, which we would expect for the number of seconds in a month. So we find that to be 30 times 24 times 3,600. Find that to be equal to 2,592,000 seconds. Times 60. And we find that to be equal to 155,552,000. What's the unit on that? What did we just calculate? Joules. We calculated the energy. Joules. That is a lot. That's like ridiculous amount. I mean, that's just one light bulb. You're charging your whole house. Okay? This is like measuring the distance from here to California in inches. It's obnoxious. It's not wrong, it's just absurd. We need a different unit. We need a mile. Okay, so does everybody understand the problem? Like, it's not wrong, it's just ridiculous. So they came up with a unit called a kilowatt hour. Okay, and so this is a kilowatt hour. This is kind of like our mile. We're going to use the same equation, but we're going to convert our power into kilowatts. This is the tip off. This is what you know to convert to. You convert your watts to kilowatts, and you convert your time to hours. Okay, so same equation. How many watts in a kilowatt? 1,000. Okay, I will give you. Okay, so let's say, like, how did you know that? If I say you've got 4K in the bank, what does that mean? 4,000. Why does the K stand for kilo? What? Light bulb. There it is. You will never forget it. You're welcome. No, that's a form. Okay. So you're dividing by 1,000. 1, 2, 3 decimal places. Good with that? 3. Divide by 1,000. How many zeros in 1,000? There you go. Okay. So that's that many kilowatts is equal to our energy over our hours. So we drop off the times 3,600. That's just 720 hours in a month. When we multiply those two, what we find is 43.2 kilowatt hours. Way more manageable. The hours in a month. So I did 30 times 24.
Oh, okay.
Good with that? That number, that's realistic. You could print that out on a bill. Okay. And so then we need to figure out how much we're charged. So this becomes more of like unit analysis. I've got this rate here. I want to end up with dollars. So I want dollars on top. And I want to get rid of kilowatt hours. So 1 kilowatt hour is 9 cents. See how that's working? So your kilowatt hours goes away, and you're left with $3.88. Yep. Okay. But remember, you don't have money. Yeah. But you're also not going to just have a light bulb on. Okay? Good with that? Okay. Last question. Yeah. But we'll keep it there. Have a conversation.
It's gonna be like F. It's gonna be actually they don't sell. Actually, they just like the idea.
It's all a facade.
It's actually totally a facade. It's actually free. But they don't.
They're just selling you air.
So they just charge you. But like actually, they don't sell anything. Electricity does not exist.
Correct answer is.
I don't know.
What do we calculate for? Energy. You are calculating you're being sold energy. Okay. Power is the rate at which your energy is being used. To bring something to somewhere you're more familiar with, when you go to the gas station, power would be the rate at which gasoline is going out of the nozzle. How many gallons per second? What you're charged for isn't how fast it's coming out. You're charged for how much gasoline you buy, you put in your tank. Does that make sense? This is the rate. This is the amount. Good with that? Okay. Crazy.